You and we can walk across a messy room, step over a curb, or, I don't know, climb a pile of rocks without even thinking about it. But for a robot, those simple tasks are an absolutely epic computational challenge. So how in the world does Boston Dynamics teach its most advanced humanoid robot to see, think, and move in our world? Well, let's break it down.
So this is Atlas. It's a humanoid robot from Boston Dynamics, and it's so much more than just a cool piece of engineering. Really, it's a research platform. It's designed to tackle some of the hardest problems out there, like disaster relief, where a robot has to navigate really unpredictable and frankly dangerous human environments. And that brings us right to the core problem. How do you actually teach a 155 kilogram, that's about 340 pounds, humanoid robot to walk over a pile of rubble without just tipping over? Well, the answer isn't some single brilliant line of code. It's all about making thousands of smart decisions every single second. And the key to making all of those decisions is this mathematical concept called optimization. Just think of it like this. It's the art of finding the absolute best possible choice from a huge sea of options, all while having to follow a very strict set of rules. This idea, optimization, is basically the engine that powers everything Atlas does. Now, the specific solution we're going to dig into comes from a brilliant team over at MIT's Computer Science and Artificial Intelligence Lab. They took this incredibly complex problem and broke it down into 3 fundamental optimized steps, and that's the framework we're going to use to really understand how Atlas learns to walk. So let's start right where the robot does. Before it can even think about moving, it has to see. This is step 1, seeing the safe spots. It all kicks off with perception. Now, Atlas's eyes aren't cameras like ours. It's a rotating LiDAR sensor. This thing shoots out lasers and measures how they bounce back to build this incredibly detailed 3D point cloud map of the world around it. It tells the robot exactly where every surface is, right down to the millimeter. Now, the real challenge here is summed up perfectly by what the researchers said. The set of safe terrain is unlikely to be convex or even connected. I mean, in plain English, that just means the real world is messy, right? Safe places to put your feet are scattered all over the place, they're uneven, and they are definitely not simple shapes. So the robot needs a way to turn that messy 3D map into simple, usable areas. For that, it uses this really clever algorithm called Iris. Okay. Imagine you're in a cluttered room and you start blowing up a balloon. That balloon is going to expand to fill the biggest empty space it can find without popping on any of the furniture. Iris does exactly that, but mathematically. It finds the largest, safest, and simplest safe zones for its feet. And you can see that process right here. Look at the image on the left. The algorithm starts with just a tiny seed point in a spot it knows is safe. Then on the right, you see it expand out like a bubble, pushing against all the obstacles until it has carved out the largest, simplest, and safest region possible. It's just a genius way to turn chaos into order. Okay, so now the robot knows where it can step. But, that's really only half the battle. This brings us to step 2, planning the path. So the planner is another optimization algorithm, but this one has a trickier job. It has to make 2 huge decisions at the exact same time. First, it's got to choose which of those safe zones it's going to aim for. And second, it has to decide the exact spot for the foot to land inside that zone. It's like choosing both the city you're driving to and the specific parking spot all in one go. But it's not just about finding any old path. It's about finding a path that's actually possible. The optimization has to respect the robot's own physical limits. I mean, Atlas can't just teleport its foot anywhere. The problem has these constraints built in, based on how far its legs can stretch and how much it can twist its body. Every single step in the plan has to be physically achievable. And here it is. This is the result of that super complex calculation. What you're looking at is the complete footstep plan, laid out right over the 3D map of the cinder blocks. Each one of those yellow shapes is an optimized decision, a perfect balance of getting closer to the goal, staying inside those safe regions, and respecting the robot's own body. It's the robot's roadmap to get across the obstacle. But hey, a plan is just a plan. The hardest part is actually doing it. And that brings us to the final and maybe the most difficult piece of the puzzle. Step 3, staying balanced. This slide just perfectly captures the difference between theory and practice. On one hand, you have the ideal plan from the optimizer. It assumes a perfect world, a totally smooth, graceful path for the robot's center of mass. But then you have physical reality, where the world is wobbly. gravity, momentum, tiny imperfections, they're all trying to pull the robot down. This is where the last layer of optimization, a real-time feedback controller, comes into play.
You can think of this controller as being kind of like our inner ear. It runs hundreds of times every second, constantly comparing where the robot is to where the plan says it should be. It uses a simplified model of the robot's physics to instantly calculate these tiny adjustments in forces and torques, that's just twisting force, to cancel out any errors, maintain balance, and stay on that planned path. It is literally what keeps Atlas from falling over.
So you've got perception, you've got planning, and you've got control. What happens when you put it all together? Well, you get a little glimpse into the future of movement.
What we've seen here, it's not just one magic trick. It's this beautiful system of optimizations all working together in harmony. Perception finds the safe spaces. Planning chooses the best footsteps. And control, well, control makes it all happen in the real world, millisecond by millisecond. Each layer feeds into the next, creating a robot that is so much more than the sum of its parts.
And the result is a robot that can confidently walk over terrain that would stop most other machines in their tracks. But what's really powerful about this whole framework is that it's not just for walking. Because it's based on the fundamental physics of movement, this same layered approach of perception, planning, and control is what lays the groundwork for even more dynamic and incredible motions, like running and even jumping.
At the end of the day, what we're seeing here is more than just a robot walking over some blocks. We're watching a machine learn to truly master movement in our own physical world. And it really makes you wonder, once they've perfected walking and running and navigating all our messy environments, what are the next great problems we're going to ask them to solve?